All right, we're in a new unit, sequences and series, and this first section is really kind of a reminder of everything you know about sequences from pre-calc, and I'll introduce a few new vocabulary and things you need to know. Okay, so reminder, a sequence is a function, but the domain is simply the set of positive integers. So if I have this sequence an is equal to n squared, it would look just like the parabola. Right here would be the function, all right, but the sequence would look like this, right? So just reminding you visually of the difference between the function version and the sequence version. Okay, so and our notation, remember, is a sub n rather than f of x. So our variable is going to be n throughout all of these. And our goal today is to determine whether a sequence converges or diverges. If the sequence converges, that just means it will approach a limiting value, whereas if it diverges, it will not. So we're going to be doing lots of limits today. All right, so when we do the limit of a sequence, we're just going to be doing the limit as n approaches infinity. All right, so we are looking at the end behavior of these sequences. All right, so if it converges, if we get the limit is equal to some number, then that's what it converges to. All right, if it does not exist, then we will say that it diverges. Okay, so as an example, remember that we've already done the limit of this sequence. And this is our, oh no, I can't think of it. But we've done this where we took the limit as n approaches infinity. And this is on page 571 if you wanted to see the whole thing. But remember, when we have a variable raised to a variable, we use the natural log, and that helps us move that power down. And then we take the sequence, or then we take the limit and all that. So all of that work is on page 571. And you can see that this limit equals e. And that's where we get that compounded continuously formula. Here's the compound interest formula, and then when we take it to infinity, compounded continuously, then that's where we get the e. So if you don't have your books out already, I would strongly suggest pausing the video, getting out your books, looking at page 571, and I will be referring to lots of examples in the book throughout this video. Think of it as kind of like a narrated guide to looking at this, these examples in this section. All right, so other examples, if you think about the sequence a sub n is equal to 3 plus negative 1 to the n power. Well, if I keep plugging in different values for n, starting with n equals 1 and so on, then I'm going to get alternating values. I'll start with 2, and then I'll go to 4, and then 2 and 4. So it's going to keep alternating back and forth between 2 and 4. So this means that the limit as n approaches infinity does not exist, because that would be an oscillating function or an oscillating sequence. So we would say the sequence diverges. And then in this example, example 2, so if I was doing the limit as n approaches infinity, we would use that technique where we divide by the highest power in the denominator. Okay, so if we do that, we're going to get 1 over n minus 2. So that's going to give us a value of negative 1/2. So here it does converge. So this would be what we say this sequence converges to, is negative 1/2. And don't forget your L'Hopital rule from the previous unit. If I wanted to see if this converged, so if I was doing the limit as n approaches infinity of this, and I plug in infinity, I'm going to get infinity over infinity. Right? So we have our indeterminate form. So that would tell us, oh, well, let's do the L'Hopital's rule. L'Hopital's rule we have to use on the function, but remember, if I can find the limit of the function, then I can find the limit of the sequence. Okay, so if I do the derivative of the numerator, that would be, let's say I'm doing the limit as x approaches infinity of x squared over 2 to the x minus 1. So now we're dealing with the function. So the derivative of this is going to be 2x over, remember this is going to be the natural log of our base 2 times 2 to the x, and then the derivative of the 1 is 0. And so now when I do this, I'll get infinity over infinity again, right? So I'll have to do this process again. L'Hopital rule. So the derivative of the numerator is 2, and then we would have ln of 2 again. So that would be ln of 2 raised to the second power times 2 to the x. All right, so now when I plug in infinity, I'm going to get 0. Okay, so because this function, the limit of this function is equal to 0, then this limit will be equal to 0. All right, so that converges. We would say that converges to 0. All right, so let's go back to your books. Okay, we're going to look at page 597. And we're going to talk about the squeeze theorem. Remember the squeeze theorem for limits. We are trying to find two functions that squeeze our original function together. And it has to be, the end behaviors have to be larger and smaller than our function. All right, so if we look at example 5 in the figure 9.2, here's what I want you to notice. Okay, in example 5, we have the sequence, okay, I'll write it up here. We have the sequence Cn is equal to negative 1 to the n power times 1 over n factorial. Okay, so that's the sequence we're trying to squeeze, and we're trying to find the limit. All right, so keep in mind that n factorial, this is what they're talking about in the book. N factorial, you know, we do 1 times 2 times 3 times 4 and so on, right? So after the fifth term, or the fourth term, so 1 times 2 times 3 times 4, that'll be 24. And then it's going to be times 5 times 6 times all the way up to n. And then they look at 2 to the n. Okay, so again, after the fourth term, so the fourth term is 16. And then I'm going to be multiplying by 2 times 2 times 2. Okay, and keep multiplying by 2. All right, so notice that as long as we're above the fourth term, that 2 to the n is always going to be a lot smaller than n factorial. All right, so if I take 24 and multiply by 5, that'll be a lot bigger than 16 times 2. And then if I do the next one, if I do 24 times 5 times 6, that will be a lot larger than 16 times 2 times 2. All right, so since factorials grow much faster than exponential functions, that helps us with this function, because if I have a factorial in the denominator, that means that that is approaching 0 a lot quicker than if I have 2 to the n power in the denominator. So what we can say is this sequence is always going to be less than 1 over 2 to the n power, as long as n is greater than 4. So as long as I have the terms greater than that. And that's like essentially what we care about when we're taking the limits. But if I also do the negative one, so these negative ones will always be smaller than the positive 1 over n factorial. Okay, so this is going to be the squeeze theorem. So both of these, the red ones, both of those functions, when we take the limit, they will be equal to 0. So then I know that this middle one will also be equal to 0. So that's what that example 5 is trying to tell us. But it's a great realization for you to see that n factorial grows a lot faster than any exponential, whether that's 2 to the n or 3 to the n or so on. So keep that in mind as you're doing other sequences involving factorials and exponentials. All right, so now I want you to look at 598. And that's the absolute value theorem. Okay, so that's basically saying if we have a sequence and we take the limit of the absolute value of that sequence, and if we know that that is equal to 0, then we know that the limit of the original sequence will also be 0. And if you think about it like this, if I have anything that has both positive and negative, so I have like an alternating sequence, okay, then we can split that up into a sequence with positive terms and the sequence with negative terms. So basically we're saying if we take the absolute value of that, we're saying, okay, all the negative ones are going to converge and all the positive ones are going to converge. So if we add them together, they will converge as well. Okay, so if we look at this one, this is the one we were just talking about. So if I just write this out the way it's written with our sequence, we have the first term is -1, then 1/2, then -1/6, 1/24, and so on, right? So this is an alternating sequence, right? It's hard to figure out what's happening here. But if I do all of the negative ones, so if I do the negative version of that, then that's just going to be the -1, the -1/6, the -1/20th, and so on. So you see how this is going to converge to 0, right? It's getting closer and closer to 0 from the left. And then if I look at all the positive ones, those are the ones 1/2, 1/24, 1/720. Okay, these are going to converge to 0 from the right. Okay, so visually, think of it this way. If I were to graph these, okay, I would start at, okay, my first term is at -1, then my second term is at 1/2, then my third term is at -1/6, and then my second or fourth term is 1/24. And so it's going to keep doing this, right? So even though it's alternating, it's getting closer and closer to 0. So if I take the limit as it approaches infinity, it will equal 0. Okay? So let's look at a few other examples from our book. I'm going to erase this so I have more room. So make sure you have that before I erase that. All right, so I want to look at how do we write a sequence based on just the terms. So let's look at, this is number 70 from this section. So if we look at the terms 3, 7, 11, and 15. All right, so reminder of how to write these, and I know you've done this in pre-calc, but it's good to have a reminder. So if we wanted to write an expression for the nth term, all right, so we want a general formula. Think about what is happening each time, right? So this is adding 4 each time, which means it's a linear. So you know that you're going to have an is equal to 4n plus, so it's like mx plus b, but it's going to be 4n plus what would be our b, because this is actually the value of the first term, right? So if we go back 1, that would be a -1 for our 0 term. So you can think of it like that, or you had formulas back in pre-calc too, you can do that, but I just like to think of it as linear because we are very familiar with linear. All right, so then like 74 has these terms, 1 and then -1/4, +1/9, and -1/16. Okay, so obviously this is alternating. So we're going to have, anytime you have alternating, you're going to have a -1 to some power. And we don't know which, we'll figure out which power in a minute. So it'll either be to the n or the n plus 1 or the n minus 1, however we want to do it. But we'll figure out what power we want to put there. And then if you notice that these are going to be, let's see, if we look at the pattern in the denominator. Did I do the wrong one? I did the wrong one. That's okay. This is actually 72. So we'll just do this one. So these are actually, if you think of this as 1 over 1, so this is going to be like this is 1 squared, this is 2 squared, this is 3 squared, and so on. So this is basically just n squared. All right, so we know we're going to have 1 over n squared. And then this first one is positive, the second one is negative. So when my nth term is odd, I want it to be positive, and when it's even, I want it to be negative. So it's kind of opposite of what we normally do with power. So I need to do like an n minus 1 kind of thing, or an n plus 1. It really doesn't matter. So I'm just going to do an n minus 1. So when my term is 1, I would have negative 1 to the 0 power, so that would be positive. And then when my n is 2, that would be 2 minus 1, so negative 1 to the first power. Okay, so just make sure you're comfortable with doing those alternating ones. And then let's see, let's look at 79. So this one is different. It is alternating. And then notice that the pattern in the denominator, it's not really factorial because it's skipping, it's only doing odd powers. And I can't just say 2n plus 1 or anything like that factorial, because factorial means I don't skip any numbers. So there's no way to really write that denominator explicitly. We can definitely do the negative 1 aspect. Okay, so I'm going to do the negative 1 up here. And since our first term is positive, we want to do a thing like what we just did in 72. So we're going to do like an n minus 1. All right, so to handle something like this, we can't write it explicitly, but we can show the pattern. So we can write an expression. So all they wanted was an expression. It doesn't necessarily have to be like what we would consider a function. And then just to show people that are using this expression how to continue the pattern, we would say that these are odd numbers, so 2n minus 1. So we just would show that we're going to continue this. The next one would be 7, and then 9, and so on. So it's okay to write it like this, and that's usually what throws people off on problems like that. Okay, so we've talked about how to write sequences as an expression. Let's go back to our book and look at what we mean by monotonic. So this is new. Make sure you are familiar with this vocabulary. So monotonic basically means that if the terms are non-decreasing or terms are non-increasing. Okay, so that's just what we mean by monotonic. Okay, so this is an important note to make. Monotonic allows for a function to stay constant as well as increase or decrease. So I want to make sure that it's not, it says non-decreasing or non-increasing because they want to include terms that are constant. Okay, so in example 8 here, that's right below that, all right, it says determine whether each sequence having the nth term is monotonic. So that first one, 3 plus negative 1 to the n, all right, that's the one that alternates between 2 and 4. So obviously that is not monotonic. It increases, then decreases, and increases, then decreases. All right, the second one, the b, is what this is referring to. We're comparing the b to the n with the b to the n plus 1. All right, so if you look at how they wrote that there, the first one there, it says b to the n is equal to 2n over 1 plus n. And then in the second part, I'll write what they have here. They have, is that less than our 2 to the n plus 1 over 1 plus n plus 1. Okay, so all we did was, instead of having n, we replaced it with n plus 1. That's how we represent the next term after n. Okay, so if we simplify that, distribute that 2 and combine like terms and then cross multiply, they're showing us that we're going to get 4n over here, 4n plus 2n squared. Over here, I'm going to get 2 plus 4n plus 2n squared. Okay, so the 2n squareds cancel, the 4n's cancel, so I have 0 is less than 2, and that is always true. So yes, this will always be true for that. So this is a very common way to decide if a function is monotonic. Okay, is to compare the n plus 1 term to the n term. Okay, so just be aware of that. You'll see that again later when we start looking at other tests for convergence. All right, so also there's at the bottom, see the note at the bottom of the page for another way to show whether it's monotonic. So it says at the bottom that if you treat this as a function and then take the derivative of it, okay, so if we treat this as a function of f of x is equal to 2x over 1 plus x, the derivative of this will always be positive. Okay, so since it's positive, since the first derivative is always positive, that means that the function is always increasing. Since it's increasing, that means that it's monotonic. So that's another more calculus way to show that something is monotonic. So why do we care about monotonic? That's what I want you to look at 601 for. We're talking about bounded sequences. All right, so bounded is exactly what it sounds, okay? If it's bounded above, then all the terms are going to be smaller than some value m, okay? That's what we call the upper bound. All right, if it's bounded below, then all of the terms of the sequence are greater than some n value, so that n is called the lower bound. And then we call a sequence just plain bounded, and that's if it's bounded both above and below. Okay, so it's pretty straightforward as far as what bound means and what we think it means. But what I really want to call your attention to is this theorem, 9.5. It says if a sequence is bounded, so that means both above and below, and if it's monotonic, which we were just talking about, then it must converge. So this is a nice way to avoid doing the limit. So we don't have to always do the limit as n approaches infinity. We can show another way by showing that it's bounded and monotonic. Okay, so keep that in mind as you're doing your homework.